Trust boundary, drawing the lines your systems depend on. Security protocols, cloud infrastructure, and the AI working behind your tools, drawn out step by step until they click. Today on Trust Boundary, how OAuth 2.0 actually works, the protocol that lets apps use your data without ever holding your password. So here's the puzzle. How can an app read your calendar or your files without you ever handing it your password? OAuth 2.0 answers this with 4 players. You, in a browser, the client app that wants access, the authorization server that signs you in for Microsoft 365, that's Entra ID, and the resource here, the Microsoft Graph API. Watch which arrows go through the browser and which never do. That split is the whole security idea. To see why OAuth exists at all, rewind to the mid-2000s. You wanted one app to read another's data, and there was exactly one way to do it. You typed your email password into the other app. It logged in as you and screen scraped whatever it wanted. Full access forever, and the only way to revoke it was to change your password, breaking every other app too. OAuth replaced that with a token. Scoped to exactly what you approved, expiring on a clock, and revocable for one app without touching the rest of your life. Every flow in this video is just a different way to mint that token safely. First, the client app invents a secret, the code verifier, and hashes it into a code challenge. Remember this, it's the trick that makes the flow safe. The app sends your browser to Entra's authorized endpoint, carrying the client ID, the scopes it wants, and that code challenge. Entra signs you in and asks your permission for those scopes. Your password goes only to Entra, never to the app. Entra redirects your browser back to the app with a short-lived authorization code. This code travels through the browser, so treat it as exposed. Now the back channel. The app calls the token endpoint directly, sending the code plus the original code verifier. Entra hashes the verifier and checks it matches the challenge from step 1. An attacker who stole the code never had the verifier, so the code is useless to them. The check passes, so Entra returns the tokens, an access token, usually a refresh token, and an ID token. Finally, the app calls Graph, putting the access token in the authorization header as a bearer token. Graph validates the token and returns your data. At no point did the app see your password. Now let's earn that PKCE step from earlier. Same flow but this time, someone is listening. Remember, the authorization code rides back through the browser, the front channel. That's the exposed leg of the journey. And codes do leak. A malicious app registered for the same redirect. A proxy logging URLs. A pasted link in a support ticket. So the attacker holds a valid, unexpired authorization code. In plain OAuth, this was game over, but the code is only half the key. They race to the token endpoint and present the stolen code. And Entra asks the one question they cannot answer. Where is the code verifier that hashes to the challenge from step 1? The verifier never left the real app. Rejected. Meanwhile, the legitimate app redeems the code with its verifier, and everything proceeds normally. That's PKCE in one sentence. It turns a stolen code into a key missing its second half, which is why it's now recommended for every OAuth client, not just mobile apps. The access token is the key that opens the API. It's short-lived, and it's a bearer token. The ID token isn't for calling APIs at all. It just proves to the app who signed in. And the refresh token is the long-lived one, used only to get fresh access tokens without bothering you again. Bearer means whoever holds it can use it, like cash. So it only ever travels over HTTPS, it expires fast, and you never log it. That single property is behind most OAuth security advice. That access token from earlier? It's usually a JSON web token, 3 chunks of base 64 glued together with 2 dots. Let's take it apart. The first part is the header, which signing algorithm, and the ID of the key that signed it. The middle is the payload, the claims. This is where the interesting facts live. And the last part is the signature. Change one character anywhere and the signature no longer matches. That's the tamper seal. Decode the payload and you get JSON. 5 claims do most of the security work. The audience claim, this token is for Microsoft Graph, and Graph will reject a token addressed to anyone else. The scope's exactly what you consented to, or read your profile, read your mail, nothing else. And the expiry, the hard timestamp, typically around an hour to 90 minutes after issue. One caveat before you rush to decode tokens in production, Graph's access tokens are for Graph, not for you. Their format can change without notice. Validate and decode tokens for your own API. Treat everyone else's as an opaque string. Put the tokens on a clock and the design gets obvious. Here are 2 hours of an app's life. The access token lives fast and dies young, roughly an hour to 90 minutes, and Entra varies it deliberately. When it expires, the very next graph call fails with a 401. That failure is not an error, it's the design working. A quick backchannel refresh, seconds invisible to the user, and the app is running on a fresh token. Repeat for weeks. The refresh token is the long clock, days to months depending on policy. It rotates on every use, and an admin can revoke it, which is how you cut a stolen session loose. An hour later, the access token has expired. The next call to Graph fails. Graph answers with a 401. So the app quietly calls the token endpoint again, this time presenting the refresh token, no user involved. Entra returns a brand new access token and often a rotated refresh token. The user never noticed a thing. The app retries with a new token and the call succeeds. That's how you stay signed in for weeks. Daemon's background jobs and sync services have no user to sign in. So the app authenticates as itself with a client ID and a secret, or better, a certificate. It calls the token endpoint with the client credentials grant and the .default scope. Entra returns an app-only token, no refresh token. When it expires, the app just asks again. The app calls Graph with its own identity. This is the split every Microsoft 365 engineer lives with. Delegated Permissions Act for a signed-in user, application permissions act as the app itself, and need admin consent. Some things can't pop open a browser or take a password on a smart TV, a command line tool, an IoT device, so the sign-in is handed off to a second device. The device asks Entra's device code endpoint to start a login. Entra returns 2 codes, a long secret device code for the device and a short human code, plus a URL to visit. The device just shows a message. Go to this URL on your phone and type in this short code. In the background, the device starts polling the token endpoint every few seconds, and for now, Entra keeps answering. Still pending. Meanwhile, you on your phone open that URL, type the short code, and sign in normally. PAWS, password, MFA, consent, all on the device that actually has a browser. The very next poll now succeeds, and Entra hands the device its tokens. The device calls Graph with the access token, exactly like every other flow. The hard part, the interactive login, simply happens somewhere else. So here's the whole map on one screen. The front channel, blue, runs through your browser. It's where you sign in and consent, and because it's exposed, nothing that travels it can be used alone. The back channel is green, is direct, server to server. It's where codes are exchanged for tokens, with PKCE guarding the seam between the 2 channels. And tokens, yellow, are the product. Scoped, short-lived bearer credentials, the only thing an API ever sees. Auth code flow, refresh, client credentials, device code, every one of them is just a different safe path to that same yellow disk. That's one boundary drawn, and there are plenty more lines to trace. If this made things click, subscribe, and here's what we're drawing next.